This will be our first lesson of Chapter 3. Chapter 3 talks about the electron, and I know in middle school you learned a little bit about electrons. We're going to delve into it much deeper here. Students will be able to illustrate relationships between electrons, light, and waves. We're going to talk about that today in regard to the relationship, how to manipulate variables, and how to solve problems for variables including wavelength, frequency, and energy. Next time we'll discuss how the position of the electron was determined. We'll learn how to write electron configurations for elements in both the ground and excited states, how to draw orbital diagrams, and finally how to interpret them. So this will be a little bit more involved than what you've seen previously. You will have quite a few new concepts in this chapter that you probably did not see in middle school. It's not that difficult, but it does involve several new concepts, so it's essential that you focus and keep up with the material. So that's your learning goal for this particular chapter. This chapter deals with electron configuration. We're going to learn about location of electrons, how they were determined, how to write electron config, and we're also going to introduce the chapter in regard to the similarities between electrons and light. So in the 1900s, chemists accepted the idea that the atom was spherical, that the nucleus contained positively charged protons, and that the electrons were around the nucleus. But to really understand where electrons are within the atom, they did quite a bit of research that involved light and the way in which light interacts with matter. You'll also see the relationship between light and electrons. And the reason why we are interested in electrons is because electrons actually determine the chemistry of the atom. So in middle school you probably learned a little bit about valence electrons. We're going to explore that in quite more detail in Chapter 5. But electrons determine the chemistry of the atom. So it was important to know where they're located because this would determine how atoms react with one another. The electron, we know from the previous chapter, has the smallest mass of the 3 atomic particles, but because it's not confined to that dense nuclear core, it actually occupies the largest volume. They are moving around very quickly, and they are not confined to a small nuclear cavity the way the protons and neutrons are. Now, light is actually an electromagnetic wave that moves through space. And when we talk about light, we typically talk about the light we see, which is visible light. We're used to that in the form of a rainbow, the whole Roy G. Biv spectrum. But visible light is actually a very small region of the entire electromagnetic spectrum. So the electromagnetic spectrum consists of radio waves, microwaves, infrared radiation, visible light, UV radiation, X-rays, comic rays, gamma rays. And going from left to right the way I've written it, gamma rays are of very high energy, radio waves of the lowest energy. That's how come you can walk around with your iPods all day and your heads don't explode. Shown here is the electromagnetic spectrum, and right here is visible light, a very small region. This video here will give you a brief introduction into the electromagnetic spectrum.
In this What Is video, we're going to take a closer look at the electromagnetic spectrum. What we see as light is only a small part of the electromagnetic spectrum. The electromagnetic spectrum refers to the many types of radiation released from stars, including our own sun. Electromagnetic radiation travels in waves. Frequency describes how many waves per second a wavelength produces. Wavelength measures the length of an individual wave in meters. Scientists describe the electromagnetic spectrum is a long line. At one end lie radio waves, with the longest wavelengths and lowest frequencies in the spectrum. A single radio wave has the length of a football field. After radio waves come microwaves, which produce more energy due to shorter wavelengths and higher frequencies. Cell phones, radar, and microwave ovens use microwaves. Next comes infrared light.
So what you're seeing now is you go from radio waves to infrared light. The wavelength is decreasing, the energy is increasing, and we're going to talk about some of these relationships. They were initially introduced in your POGL packet on electrons and light that you were given earlier this week. Go ahead.
Sun, fire, living creatures, and other heat sources all produce infrared light. While we cannot see infrared light, we feel it as heat. Visible light occupies a narrow slice of the electromagnetic spectrum, nestled between infrared and ultraviolet light. Red wavelengths have the lowest frequencies and longest wavelengths of visible light. As you move from red through orange, yellow, green, blue, and finally violet, wavelengths shorten and frequencies increase. From visible violet light, we move into ultraviolet frequencies. Human skin produces vitamin D when exposed to ultraviolet light, but excessive ultraviolet light causes sunburns. Next, X-rays, which pass through soft tissue but not denser materials such as bone, making them valuable for medical tests. X-rays also have security applications such as airport baggage check. Gamma rays produce even shorter wavelengths, higher frequencies, and more energy. In comparison to the football field-sized wavelengths of radio waves, gamma ray wavelengths are as small as atom nuclei.
But that was always how to any advice for you.
So from the video, again, you saw that the visible light region is a very small portion of the electromagnetic spectrum. Shown here, radio waves through gamma rays. The wavelength decreases as you go from left to right. The frequency and the energy are going to increase as you go from left to right. And we'll talk about some of those relationships between wavelength, frequency, and energy in just a minute. One thing I do want to mention is if we went back into this video, this is just of interest. If you consider the visible light region of the electromagnetic spectrum, here's red, here's violet, and in the infrared region where we see visible light, birds, for example, see red light only of the visible light region, and they do see infrared. So, for example, if you have blue petals or purple petals on a flower, they're not seeing the color, they're just really sensing the scent of the flower. And bees actually see in the violet and UV light range. So the old myth that you shouldn't wear golden...
Please pardon the interruption, Dr. Kalish. Has Sydney Rott left yet?
Yes, she has.
Thank you, ma'am.
So bees, for example, see violet light and UV light, and so that old myth that yellow and black clothing shouldn't be worn because it attracts bees is just that, a myth, because they don't see yellow light. They see in this region at the edge right here. Now, electromagnetic waves, along with water waves that you would see at the ocean, sound waves that you hear, do exhibit certain common characteristics that she touched upon very briefly. The first property of waves that we want to mention is the speed of light. And you would have seen this in the POGL packet as well. All waves in a vacuum move at the speed of light, abbreviated with this lowercase c. This is a constant, 2.998 times 10 to the 8th meters per second. All constants will be provided to you. They are on the back of your periodic table as well. Here's the speed of light right here, designation C. So this is a constant that will be provided to you. You don't need to memorize it. Another property or common characteristic of electromagnetic waves is their wavelength. The wavelength, abbreviated with this lambda, is the distance between equal points on a continuous wave. And this must be in meters. You'll see in your calculation that the wavelength must be in meters. When we think about wavelength, if you look at this sine curve shown on the screen, the wavelength of this sine curve is from the beginning until it has one complete cycle. So this distance would be its wavelength, and that must be in meters. The number of waves that pass a stationary point in 1 second is the frequency, abbreviated with that V. So if you went to the beach and watched the waves crash into the shoreline, if you counted how many waves passed a certain point, say in 10 seconds, and then divided by 10, you would get the frequency, the number of waves that pass a stationary point in 1 second. The relationship between these three variables can be established with this equation here. We have the speed of light is equal to the wavelength times the frequency. And I do want to review some concepts in regard to proportionality with variables. I think this will help you quite a bit in here and in math as well. So the first thing I want to mention, speed of light is equal to the wavelength times the frequency. The speed of light is a constant. So if I set up any old equation where I had the constant is equal to x times y, and let's say my constant is 20, and we're going to set x at 4. What would y be? 5 is correct. My constant has to stay the same, and let's say that x decreased to 2. What would y be? 10 is correct. So x decreases by a factor of 2, so y must increase by a factor of 2. When you multiply two variables together, and I'm sorry, I wrote F here, and typically you make a V. This should be a V. I'm going to rewrite this right here. When you multiply two variables together, they are inversely related. Inversely related. As one goes up, the other goes down. In contrast, if you divide two variables and set them equal to some constant, if you increase one, the other will increase by the same factor. For example, if my constant is 1 and my x is 6, what would my y be? 6 is correct. If my constant is 1 and I decrease x to 4, what would y be? 4. So these will decrease by the same factor. When you divide two variables, they are directly related. When you multiply two variables, they are inversely related. They behave oppositely. And as we get into the problem solving, you'll see that understanding this concept will be crucial. Questions at this point? Okay, so what exactly is the relationship between light and electrons? And that was established by Albert Einstein with the photoelectric effect. We're going to see that when a surface of polished metal is struck by light of a certain frequency, electrons are ejected from the surface of the metal. And we can see this in the following demonstration. The metal we're initially going to put here is sodium. I've got a light source here. Initially, I'm in the violet range, lower wavelength than most of the visible light region. If I increase the intensity, when the light hits the polished metal, it ejects an electron. This is dependent on the intensity as well as the wavelength of the light. If I decrease the wavelength, you'll see that more electrons are ejected. If I increase the intensity, you'll see that more electrons are ejected. Now, if I have an intensity of about 80 and now I increase the wavelength, you'll see electrons are ejected much more slowly, and in the yellow region, you're not going to see electron ejection. So the photoelectric effect. This is also metal dependent. So sodium, when you've got a wavelength of about 392 nanometers and an intensity of 80, you're seeing electron ejection. If you replace the sodium with zinc, you're not seeing it with the same wavelength and intensity used. If you go into the UV region, you will see some. And the metals do have different properties in regard to electron ejection. So this is the photoelectric effect. You shine a light source on a polished metal surface, and in some instances you'll get electron ejection. And basically everything I showed you is listed here. Photons are the fundamental particle of light, the most visible portion of the electromagnetic spectrum, and photons have a unique property in that they're both a particle and a wave. So we can link light to electrons through the photoelectric effect, and understanding waves will help us better understand electron behavior. We established that the wavelength and the frequency are inversely related. We're going to also look at the direct relationship between energy and frequency. So the energy of a photon at a particular frequency or wavelength can be calculated. Energy has a unit of joules. H is known as Planck's constant. So that's a constant that will be provided to you. That one also is on the back of your periodic table. Energy and frequency are directly related. So those gamma rays with very high energy also have very high frequency. And that relationship is further established here. We're going to look at the relationship between wavelength, frequency, and energy in regard to the electromagnetic spectrum. Radio waves going to have the lowest energy. Again, that's why you can walk around with your iPods all day. The largest wavelength, the smallest frequency, smallest energy. As you go down here from radio waves to gamma rays, you see the increase in energy the increase in frequency, the decrease in wavelength. And again, that football field size wavelength for radio waves, the largest wavelength, shows you that relationship further. What we want to be able to do is we want to work through the problems shown here to make sure you understand these properties of waves and in turn properties of electrons. We're going to work through these problems very meticulously so that you understand how to approach them, and your classwork will further provide you with an opportunity to master these concepts. Questions at this point?
When you shine the light on those metals, why are electrons why do they eject?
You tell me.
I don't know.
So what is it about light that results in electron ejection? Look it up. You've got your Chromebooks. Look it up. Tell me what it is.
Light acts as a stream of particles that knocks electrons out of the atoms.
Why?
Are they positive? Assist.
Who's got it? Go ahead.
Because the energy of the light is higher than the energy of the atom.
And so it dislodges it. Mm-hmm. Good job. All right, we're going to work through a series of problems to explore this relationship. In the first problem, and again, we're going to be dealing, let me write these here on my paper, we're going to be dealing primarily with two formulas, and then we'll derive a third. The speed of light is equal to the wavelength times the frequency, V for frequency. Energy is equal to Planck's constant times the frequency. Those are the two formulas we're primarily going to deal with. We'll derive a third at the end. The first problem says that a helium neon laser emits light with a wavelength of 633 nanometers, and we want to calculate the frequency of this light. Whenever I see a word problem, I read through it carefully and I pull my variables out. The wavelength is 633 nanometers. We're looking for the frequency. Which formula should we use? The first one is correct. We've got the speed of light is equal to the wavelength times the frequency. I want to solve for frequency, so I'm going to divide both sides by the wavelength. And I've got the frequency is equal to the speed of light over the wavelength. The speed of light is a constant provided to you on the back of your periodic table. The unit is meters per second. They gave us the wavelength in nanometers. We need the wavelength in meters. You should recall that 1 meter is equal to 1 times 10 to the 9th nanometers. I'll give you that conversion. And then you can convert nanometers to meters by dividing by 1 times 10 to the 9th is 6.33 times 10 to the negative 7th meters. I'm going to plug that in here. You need the wavelength in meters, so the meter cancels with the meter as part of the unit of speed of light. You've got 2.998 EE8 divided by 6.33 EE negative 7. We talked about calculator usage earlier in the year. And the frequency is 4.74 times 10 to the 14 seconds to the negative 1, which is also known as hertz. That's a little tricky. It's very often given as hertz. It's easier to do as seconds to the negative 1. Make sure your answer makes sense. When you divide, you subtract exponents. So 8 minus negative 7 is to the 15th. When you divide this, it's less than 1, knocking it down to the 14th power. But make sure your answer is in the ballpark so that you haven't made a calculator error. Now, if you have that multi-view calculator, you will need the denominator in parentheses or you're going to have issues. Be careful there. Pretty straightforward. Pull your variables out. Figure out what equation to use. Plug in your variables, making sure the units sync. If not, do a conversion and solve. We're going to do another one similar to it.
On this calculator, I got 10, 11.
So in your calculator, you want to punch the following. 2.998 EE8 divided by 6.33 EE negative 7 equals. Remember, instead of the times 10, you're using the EE button. So you're not hitting times and you're not hitting 10, you're just hitting the EE button. Allison. 633 divided by 1 EE9. This is like one big fraction, so you divide. Is that?
So we could put seconds to the negative first power or HC, doesn't matter which one we put.
Correct. That was your question too? Okay. We're going to do several. It'll click. The second problem is very similar. You have it in front of you, so I won't flip screens. On number 2, it says calculate the wavelength of X-rays. So we want to know the wavelength in nanometers. And the frequency is 4.80 times 10 to the 17 hertz. Hertz is the same as seconds to the negative 1, and it's probably going to be easier to work in the seconds to the negative 1 unit. Speed of light is equal to the wavelength times the frequency. How do I solve for wavelength? Divide by the frequency. So I have the wavelength is equal to the speed of light over the frequency. The speed of light is a constant. The frequency is 4.80 times 10 to the 17. I said it's easier to do seconds to the negative 1 because you see the cancellation of those units. You have 2.998 EE8 divided by 4.80 EE17. And that is 6.25 times 10 to the negative 10 meters. But they asked for it in nanometers. Knowing that 1 meter is 1 times 10 to the 9th nanometers, how are you going to convert meters to nanometers?
You put the 1 times 10 to the 9th nanometers on top.
You got it. And why did you do that?
Because I remember like the top needs to like equal like what the number at like the very end is, like at the very right. See it like it says nanometers right there. And so like they don't cancel out.
Okay, so he knew that he wanted to get to nanometers, so he needed nanometers here. In addition, you need those units to cancel. And what you have then is 0.625 meters. I would like you to do the problem in your notes to see if you've got some understanding of this concept. The problem is at the top of the screen. See if you can do it. Make sure you pulled your variables out properly. Make sure you solved for the variable properly. And then once you have your answer, you can check it off mine. See if you're getting the correct answer. It takes a little practice, and you're going to have 8 problems of practice over the weekend to make sure you master this concept. Something's not right. I'm thinking you put positive 7 in here. Did you get what I got? Yes, yes? Yes? Good. Go ahead, Elise.
So I can get like the division and all the numbers right, but I can never get the 10 to the
Okay. So what you have here is, wait a sec, I'm confused.
Like I don't know how to figure out the number after the 10.
This?
Yeah, it doesn't come up in my
In which calculator you have? That should be a straight shoot. Instead of the times 10, you should be hitting the EE button. Are you not? Ready? Punch with me. Guys, we're not done yet. 2.998 EE8 divided by 9.81 EE negative 7. Did it come out this time? Okay? Okay. So that shows you the relationship, the inverse relationship between wavelength and frequency. Those radio waves have a large wavelength and a small frequency. We also want to look at the relationship between energy and frequency. And that is a direct relationship between energy and frequency. As the frequency increases, the energy increases. So we're going to take a look at this relationship here. This one's going to be pretty straightforward, probably a little easier than the first one. Question 3 says calculate the energy of a gamma ray photon with a frequency of 5.02 times 10 to the 20th hertz. So we're going to pull the information out. We want to know the energy. The frequency is 5.02 times 10 to the 20 hertz. And remember, hertz is the same as seconds to the negative 1. Energy is equal to Planck's constant, which is provided, times the frequency. So energy is equal to 6.6262 times 10 to the negative 34 joules times seconds times 5.02 times 10 to the 20th seconds to the negative 1. The seconds to the negative 1 cancels, and I'm going to multiply those two quantities. And again, EE instead of times 10. And I have 3.33 times 10 to the negative 13 joules. Is that what you got as well? All right. So this is pretty straightforward. Planck's constant times the frequency. Number 4 is grossly similar. It says, what is the difference in energy between a photon of violet light with a frequency of 6.8 times 10 to the 14 hertz and a photon of red light with a frequency of 4.3 times 10 to the 14 hertz. So we're looking for the difference in energy between these two photons. How would we go about determining that? Exactly. You find the energy of each one and then you subtract the two. Take a few minutes to try and do this problem. got it? What'd you get? What'd you get? What'd you get? What'd you get? What'd you get?
4.6 times 10 to the negative 19.
Almost perfect. So when you worked it, you wanted to get down to 2 sig figs because they gave you those frequencies in 2. So for violet, for red, subtract the difference. Delta means change in or difference. And you get 1.7 times 10 to the negative 19 joules. So pretty straightforward. It does require practice, and you will get quite a bit of it over the weekend. I'm guessing it'll take you about a half an hour to do those 8 problems. The very last thing we want to do involves substitution, just like you did in algebra or even in pre-algebra back in middle school. We know that the speed of light is equal to the wavelength times the frequency. We can see the inverse relationship between the wavelength and the frequency. We know that energy is equal to Planck's constant times the frequency. I want to derive a new equation with energy and wavelength. If I solve this one for frequency, which we've already done, I can substitute this piece in right here, and as a result, I can derive a new formula with energy in it and wavelength in it. This is a derived formula showing the inverse relationship between energy and wavelength. So if they give me wavelength, with one equation, I can solve for energy. This equation is very easy to derive and very easy to remember because you have both constants in the numerator. So you've got energy is equal to Planck's constant times the speed of light over the wavelength. And we're going to use this formula to solve problem number 5 together. Number 5 says calculate the energy of a photon of UV light with a wavelength of 49 nanometers. We know that energy is equal to Planck's constant times the speed of light over the wavelength. I'm going to substitute now, or just plug in. Planck's constant is 6.6262 times 10 to the negative 34 joules seconds. Speed of light is 2.998 times 10 to the 8th, that's a sloppy 8, sorry, meters per second. But what about the wavelength? What unit must the wavelength be in? Meters. So you've got to convert that the same way we did previously, and that's 4.90 times 10 to the negative 8 meters. And I'm going to plug that in here. I've got both constants on top. And I've got an energy of 4.05 times 10 to the negative 18 joules. And let's review what we did there. We used our derived formula that has both constants in top. We divide by the wavelength, which must be in meters. So I converted my wavelength of nanometers to meters. I plugged it in here, and this photon of UV light has an energy equal to 4.05 times 10 to the negative 18 joules. Two last things I want to mention. Either before the bell rings or at home, you should try and do number 6. I will give you the answer to number 6 so that you can check your work. The answer to number 6 is right here. 3.41 times 10 to the negative 19 joules. And for Monday, those part 1 of your classwork, it's 8 problems similar to what we've done today. We still have about 3-4 minutes till the bell rings. I ask you to please put your Chromebooks away. We've started to establish a relationship between electrons and light.